Hello, good morning. Today I will talk about noise reduction technologies. There are two types of noise reduction technologies. One type are spatial domain technologies. Another type are frequency domain technologies. For the frequency domain technologies, it's a little difficult, so it's beyond this course. We will focus on spatial domain technologies. The basic idea of spatial domain technologies is to design a filter to filter out the noise. So how to design a filter and how to use the filter is what we need to do. For design the filter, it's also beyond the course. We will focus on how to use the field designed by other people to do noise reduction. In order to understand the basic idea for spatial domain noise reduction technology, we need to know some basic concept for noise reduction. The first one is called discrete convolution. In fact, discrete convolution has 2D and 1D operation. For 2D operation, it's for image. For 1D operation, it's for signal. We will start from 1D because 1D is simple than 2D. So for a digital signal, Fi, when you guys talk about digital signal here, we just assume that this is a sequence of number. For example, we can say if, start from negative infinite or something, then go to f100, f negative 100, f negative 10 or something, then go to negative 3, negative 2, then even negative 1, then f0, then f1, then f2. So don't think it's difficult. It's very simple. We just assume that it's a sequence of numbers. We represent by f. So that's for the signal. There are a bunch of examples for signal. For example, there is some number from two real numbers, 100 or 156 or something, 0, even negative sometimes, it's a series of numbers. So we call it's a digital signal. Here we assume that the signal frequencies are infinite. That's a talk about the digital signal. So for this digital signal, sometimes also this digital is noise. For example, you have audio, the audio, perhaps sometimes there is noise there, this is the audio, audio sequence. So sometimes there is noise there. You need to remove the noise. So you design a filter, we call the edge. Then perform the edge on the signal. Then remove the noise. The field here also we assumed that it's infinite. For example, we can write the edge as follows: edge negative infinite, then go to then 1h negative 100 or something. Okay, just go to h negative 3, h negative 2, then h negative 1, then h0. Okay, then h1, then h2. Okay, also go to positive infinite. So that's explain two infinite sequence of numbers. So we have these two things. Then their discrete convolution of sequence f and sequence h is also an infinite sequence and can be explained as follows. Okay? So for each element in the discrete convolution of f and h, okay, we labeled as g. Okay? For gi, we can obtain use this symbol. This star here we called convolution symbol. It's not the multiplication symbol in our math. Okay, we call this one convolution operation. So this convolution operation is defined as here. Okay, this symbol called summation. If you guys don't understand the meaning, you can expand it. Okay, is equal to f infinite, then h, okay, I minus negative infinite, so it's plus infinite. Okay, you can go on. Okay, do them step by step. Go to f, okay, negative 3, then should be h I minus negative 3, so it should be plus. Okay, then f negative 2 should be h plus 2. Okay, then f negative 1, okay, h I minus 1. Then go to f0 multiply h0. Okay, that's important. Okay, let's use another pen. I'm sorry. Let's see whether we can change the change ink color. Okay, we change the blue. Okay, so you guys see here h0 f0 multiply h0. So this is the key term. So plus f1 multiply, oh no, I'm sorry, here should be I plus 0. Okay, I plus 0. Okay, because when we go to f0, hi minus 0. Okay, so it should be hi here. Then still you can go on f1 multiply h1 I minus 1. Okay, you can go ahead f2 multiply minus 2. Okay, we just go ahead and go to infinite f infinite multiply h minus infinite. This is the expansion of this term. Okay, in fact I assume that you guys know the summation because you learned from high school. Okay, also this term you can write in the follow format. These two and these two are the same. The only thing here is h hat equal to h negative I. Also, if you expand this one, use the same way here, you will find this extension equal to this one. Okay? The only things we use h hat I equal to h negative I. Okay? So this is this convolution of gi. How to get the gi? So I can from negative infinite to positive infinite. This is for digital signal with infinite length. However, in real application, the signal and the filter are finite. For example, if I should from some negative n place to positive place, okay? So you can write the f as f start from negative n1, then f negative 1 plus 1, so go ahead, go to f0, then go to f1, f2, then go to fm2. After n2 plus 1 is still there. The only thing we assume that they are 0. Okay, you can say it's 0 after that one. And before negative n1, also we say the f value is 0. Okay. For the h is the same. Okay, h should be from some m1. Okay, then m negative n1 plus 1, then go to h0, then go to h1, then also stops from some place. Okay, m2. The situation is the same as if we assume that before negative m1 is 0, the h value is 0. Okay, after that also is 0. So in fact this case is the special case when the signal assumed at infinite. We know we can use this math equation to write some program to compute gi in finite case. Okay? How to do that? I will show some example. The first example is the filter is h start from negative 1, okay, equal to 1/4. h0 equal to 2/4. h1 equal to 1/4. For h2, h3, we just assumed it's 0, so we don't need to think about. Before the negative 2, also is 0. For the signal f, we assume that f0 equal to 1, f1 equal to 1, f5 equal to 1, f6 equals to 2, f7 is 2, f9 equal to 1. So f10, f11 is 0. Okay, then this is f negative 1 is 0, f negative is 0. Go to this direction also is 0. Both of them are finite. So how to get a GI? Definitely we can use the formula shown in previous slides. Okay, to do that. For understand the concept, we can use a simple way. First, let you understand how the equation work. Okay, we write the h as follow. Okay, h has 3 value. Then we write the f also show here. Okay, then how to get the g? First, let's know how to get g1. Okay, in the equation, the I will be equal to 1. Okay, I equal to 1 if you replace the I here. Okay, for example, replace the I here, so f0 should be multiplied by h1. Okay, so f0 should be multiplied by h1. That's we based on the math equation. Okay, that's first things. Then you guys see h2 should be multiplied if negative. Okay, then f1 should be multiplied by h0. Okay, then f2 should be multiplied by h negative 1. Okay, so let me change the pen. See here. Okay, this is get the g1. So see here, f negative 1, f0, f1, f2. That's the f is from the negative to the positive, but h is from the 2, 1, 0, negative 1, from the positive to negative. That means h and f, they have different direction. Okay, when you do the convolution, first we just arrange the h from positive to negative direction. Okay, but for the f, we are from the negative to positive direction. Okay, that's two direction. Okay, this is f0. Okay, this is f1. Okay, this is f2. Okay, this is f3. Okay, we just go for f4, f5. Okay, based on here. Okay, this equation, f1 should be multiplied by h0. Okay, so the h0 need to multiply this one. Okay, that means this one multiply this one. Then the h negative 1, okay, will multiply 2. Then the h1 will multiply h1. Okay, then you will do this multiply 1 plus h0 multiply 1. Okay, plus this one multiply this one. Okay, then you will get g1 as follow. Okay, if you guys do the simple mathematics, should be good 5/4. Okay, that's g1. Now let's talk about how to get g2. In order to get g2, you need to do the similar things as you did to get g1. The first things you need to do is to shift the whole edge to right. Okay, see here, that's h0. Okay, this is h negative 1. Okay, this h positive 1. Then this is f2. Okay, h0 need to point to f2. Okay, this f3. Okay, this is f1. Then you multiply this one with this one. Okay, then multiply this one with this one, multiply this one and this one, then add the products together. Okay, equal to this multiply this one. Okay, plus this one multiply this one plus this one multiply this one. Okay, if you compute this one, you will get this value. That's the G2. Okay, if we want to get G3, okay, G3 do the same. First do the shift. Okay, make the H0 point to F3. Okay, see here. Okay, that's the, this is F3. Okay, still this is F0. Okay, so this is H0. H0 need to multiply this one. Okay, H negative 1 will multiply F4. Then H1 multiply F2. Okay, you just do the same computation, you will get this value. That's G3. Then you can do G4, G5, G6. Okay, every time go to do. Okay, use the similar way. You can also get other G, such as G4, G5, G7. But for G8 and G0, how to do that? Let's see how to compute G0. In order to compute the G0, you need to move the H0 to point to the F0. Okay, see here. That's the H0. Okay, this is the F0. Okay, if you want to compute the G0, you need to point the H0 to the F0. Okay, then this the H negative 1 will multiply F1. Okay, the question is H negative 1 because we don't have value here. Okay, we don't have value F negative 1. As we talked just now, F negative 1 we assume that it's 0. Okay, it's 0. Okay, so when you do computation, you will get H negative 1 multiplied 0. Okay, then H0 is 4. H0 is 2/4. Okay, multiple 1. Okay, then 1/4 multiplied by 1. Okay, then add them together, you get G0. So you will find G0 is 3/4. Okay, the same you can get the G8. In order to get G8, then you move the H0 2/4 here. Okay, then 1/4 here, then 1/4 here. Okay, then you multiply 1/4 multiply 1 plus 2/4 multiply 1 plus 1/4 multiply 0 because we assume that it's 0. Then you will get G8. That's G8. Okay, let's talk about discrete convolution in 2D, because what I'm doing is image processing. Image is a 2D signal. So we assume that an image is Fij, is a matrix. Then H is a matrix. Okay, it's Ij means it's a two-dimensional. Okay, the same as our matrix. So if we want to get the convolution of the F and H, okay, we name this convolution as G. We want to get a Gij, we can do the convolution Fij star Hij. This is just a symbol. Okay, then this symbol is defined as this one. Okay, Also, you can expand it. This is similar to the one-dimensional. I'm not sure you guys know how to expand it or not. First, you just expand inside, okay? After inside, then expand outside based on the I prime, okay? This format can write the second format. This is similar to one-dimensional. I think this is a high school mathematics. So let's have an example. Because this is assumed the I and j are infinite, but for the image it's finite. Okay? Let's talk about the case in finite. Let's assume that image F, okay, is a 3 by 3 matrix. The same for the H also is a 3 by 3 matrix. Generally, in real case, the F perhaps is very big. F can be 100 by 100, okay? But the H generally is small, okay? H could be 5 by 5 or 3 by 3, okay? But for this case, we just also put the F to be small, okay? So we can understand the basic idea. So see here, this is this element is H -1, -1, okay? We have two labeling here. One is X coordinates, one is Y coordinates, okay? For this, it's H -1, 0, okay? For this one, it's -1, 1, okay? -1, 0, 1, okay? For this one, it's H0, -1, okay? For this one. Then H0, H0, okay? That's this one. Then H0, 1, then this one. Then H1, H1, -1, okay? Is this one. Then H1, 0 is this one, okay? Then H1, -1 is this one, okay? Oh, no, not, I'm sorry, this is a positive one, okay? So that's H. For F, we just use the normal labeling. For example, this one we can label as F0, okay? Then this one, F01, okay? Then this one we labeled F02, okay? Then for this one, it's F01, okay? F10, I'm sorry, F10, okay? For this one, it's F11, then F12, okay? Then also we have F20, F21, F22, okay? So this is 3 by 3 matrix. So how to do the conversion of these two? Let's remove the label, okay? Oh, I'm sorry. Let's remove the label. Okay? How to do the convolution? So when you do the convolution, okay, this is F. You want to get the G the same size as F, okay? So first we do get the first elements, okay, in the G. So in order to do that, for this one, you first need to reverse the matrix, okay? Put the bottom to top, right to left. So see here, will be 1 to 1, 0, 0, 2, negative 1, negative 2, negative 1. Why we need to do this processing? Because if you guys see the one dimensional, you are found here, okay? Also it's reversed, okay? Start from 1 to the negative. But for the f, it is from negative to positive. So we need to reverse the h. After you reverse the h, okay, then if you want to get the first elements, then overlap the center with the first elements. Then you do 0 multiplied by 1, okay, 0 multiplied by 2, negative 2 multiplied by 4, negative 1 multiplied by 5. But outside the f, for this kind of area, we just 0. So 1 multiplied by 0, 2 multiplied by 0, 1 multiplied by 0, 0 multiplied by 0, negative minus 0. Then add them together, we get 13. Okay, that's for the first one. If we want to get the value in this location, then we move the center to point to the corresponding location of f. Okay, then do the whole multiplication, then the addition, then we get this one. Okay, if we want to get the third elements, okay, you move the center, okay, to point to 3, okay, then do the multiplication. Okay, for example, for this one, it's 1 multiplied by 0, okay, because outside the f, we assume it's 0. Then plus 2 multiplied by 0, okay, then plus 1 multiplied by 0. Then we do here, okay, this one will be 0 multiplied by 2, okay, then 0 multiplied by 3, okay, then 0 multiplied by 0, okay, then plus negative 1 multiplied by 5, okay, plus negative 2 multiplied by 6, plus negative 1 multiplied by 0. If you compute them, you will find it's negative 17. It's here. Okay, so that's the example for the convolution. For the real convolution, okay, the f, as I talked just now, will be very big. H generally is small. Okay, generally we call this H template. It's called the kernel. Now we know how to do the operation of digit convolution. In order to do the digital convolution, we need to design a filter to filter the noise in this image. So the design of the H is important. In the past, they have developed many filters. Mean filter is one of them. Okay, the mean filter is the mathematics is here. Okay, if the H size is m by m, okay, then you just need to add some value together, then divide by the mm. For the GST, we generally assume it's 1. Okay, so generally we just say m1. Okay, for example, for the 3 by 3 H, the H matrix is like this one. Okay, if for the 5 by 5, okay, you can get 5 by 5. Okay, 1 2 1 2 3 4 5. Okay, 1 2 3 4. Okay, then for the 5 by 5, then should be the value for each in H is 1/25. So you put the 25s here, 25s here, 25s here, 25s here. Okay, everywhere is 25. Okay, also you can 9 by 9, 7 by 7. Generally, we use the odd size. Okay, we rarely use 2 by 2. So this is a 3 by 3. How does this work? Okay, let's see here. So this is show the edge. Okay, let's get the pen again. Okay, this is the edge. I just move the one lines out. In fact, you can put it inside. If you put it inside, the inside should be one length. Okay, outside the inside is the same because you guys know the matrix operation. You can move this outside and inside. So this is the image. Okay, how to use this filter to filter noise out of this image. Okay, we need to do this convolution operation. Okay, for example, first we want to get this element. About others we will talk about later. Okay, how to get this one. Then you can overlap this edge to this. Okay, because the center of this one needed to curve the center of this one because this is correspond here. Okay, okay, then you get what? I'm sorry, let me remove this one. Okay, okay, then get this one. Okay, we get this one. Okay, you just do the convolution with this one. Then also you want to get this one. Okay, this edge will do the operation. Okay, to overlap with this rectangle. Then do the multiplication of the corresponding elements. For example, you do the multiplication with this one to multiply this one to multiply this one to multiply this one to multiply this one you will multiply this one multiply this one multiply this one will multiply this one, then add them together, then you will get this one. Okay, get this one. For others it's the same. Okay, you can do the last one, you get this one. Okay, okay, then you compute them to get the whole this one. After that, you need to think about the boundary. Okay, for the boundary, as we know, if we want to get this one, let's talk about just one. Okay, get this one. Then you put the center h1 will be multiplied by this one. Okay, then this one will be multiplied by this one. Then this one will multiply this one. Then this one will be multiplied by this one. But for others, because outside is not defined, we assume that it's 0. So it's 0. So don't need to do anything. Just multiply this 4 with this 4. Okay? Then you get this pixel. For others on the boundary, we do the same thing. Okay? What's the mean field really do? For example, we think about this pixel will be replaced by the average of this 9 pixels. That's the reason we call it mean field. Sometimes we call it the average field. Okay? For example, this is 0, 1, 3, 4, 2, 2, 1, 0, 1. If you add it together, then divide by 9. Then you will get this one. Okay? Then will be 13. Divided by 9 will be here. Thus, the basic idea of mean field is to use the average of the nearby pixel to replace the pixel value. This is for the real noise reduction. For example, we have some image Okay, then we put some Gaussian noise there. Then we put some solid and paper noise there. Okay, then we use the 3x3 mean filter to do the filter. Okay, then use 5x5, then use 7x7 filter. That means this H, the size of H is 7x7. So you guys see here, okay, if the size of the filter is smaller, some noise is there, okay, it's still there, okay, noise is there. But with the large size of the filter, you will find the image will be blurred, okay, for mean field. So how to select the size of the mean field is important. Besides the mean filter, we also can use Gaussian filter. Gaussian filter is designed by other people. You can use this equation to get the H. Okay. Also, we call the H filter. Okay. In fact, this is a Gaussian shape. There are two parameters you need to determine when you compute H. One is valence sigma. One is parameter C. Okay. You need to select the C and the valence when you design this field. In MATLAB, they will let you to input the C and the sigma. Then you can get the H. Okay. So this just shows use a Gaussian field to field the image. Okay. You will find the Gaussian field works better than the mean field. See, this is blurred for the same size Gaussian field. This looks good. Okay. If the noise in the image is Gaussian noise, then use Gaussian field will get a better result. Median field. Beside the Gaussian field, mean field, another field is called median field. Median field is not related to the convolution. In fact, a median field operates over an m by m region by select the median intensity in that region. We will see the advantages a median field could have over mean field. In order to understand how does a median field work, we need to understand some concept called labels of a pixel. Let's consider this pixel. What are its labels pixel? This one, 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 this one. Yes, that's the basic concept. But it is a little complex. In image processing, when you talk about the labels of a pixel, we have different concept, different type of labels. One type we called 4 labels of a pixel. 4 labels pixel, that means the labels of this pixel are means this pixel, this pixel, this pixel, and this pixel. Okay, so we called these 4 pixels are the 4 labels of the pixel P here. Okay, in image processing, we also call this neighborhood is 4 neighborhood. So in this 4 neighborhood, include 5 pixels. It's not just include this one, this one, this one, this one, also include itself. Beside the 4 labels of pixel P, okay, 4 labels include this kind of pixel. We also have 8 labels of pixel P. 8 labels pixel P means the 8 pixels around the pixel XY. So include the whole 8 pixels, okay, near this pixel. So we totally have 9 pixels in the label. After you have this concept, then we can discuss the medium field. Let's have an example, okay? This is the original image. You want to perform medium filter to get a noise reduced image. You need to perform median operation. For example, for this pixel, its 8 labels are inside the dotted rectangle. Okay, so we have 9 pixels inside this label, including itself. So in order to get the new pixel in the noise reduced image, we first do some median operation. Just list these 9 pixels based on the order. Okay, we have 3 0, so 3 0 put first. Then is 2 25. Okay, we have 3 2 25. Then 3 2 26. Okay, let's get the order. Then we get the median value. The median value is here. Okay, 255. After you get the median value of the sequence, then the new pixel value in the noise reduced image should be 225. Okay, see here, 225. So this pixel become 225. Definitely, you also can talk about this pixel. Okay, if we talk about this pixel, we need to check what it should be in the new image. So also you do the same sorter. Okay, you get the 8 pixel neighborhood. Okay, this one. Then you sort the pixel 0 to 26. We have how many to the let's do this way. Okay, let's put here 0. Then next is 2 26. Okay, we have 1 2 3 4 5 6 7 to 26. Okay, to 26. One, 2, 3, 4, 5, 6, 7. Okay. Then the biggest value is 255. Then you get the median of this number of sequence. Then you definitely will find the median value is 226. So in the new image, the 255 will be replaced by the 226. Okay? For each pixel, you do the same operation. Okay? Then you will get the noise reduced image. That's how median field work. Let's compare 3 field, mean field, Gaussian field, and median field. What's the performance when they are used to reduce the Gaussian noise in the image? This is got by mean field. This is got by Gaussian field. This is got by median field. So for the Gaussian noise, you found this is better than mean field, also it's better than median field. For the image you got use median field, you will found there is some noise here. Okay, the same you guys see compare here. Okay, the Gaussian field looks better, okay, than median field and mean field. When the field size is 7 by 7, we compared these three ones. See, this mean field got blurred. This median field also got blurred, but the Gaussian field works better. Okay, that's for the Gaussian noise. If the image are noised by solid and purple noise, then you use these three filters to perform noise reduction. This is show the result. When the size of the filter are 3 by 3, see mean field the noise is still there. For Gaussian filter the noise is still there. But for median filter, see the result is much better than mean field and Gaussian field. Compare the field with the other sides, they have the same. Okay, you will find median field is better. Okay, so median field works better on solid and purple noise than mean field and Gaussian field. That's the advantage of median field. MATLAB provides many functions for image noise reduction. You guys can go to this website. Okay, see, go to this website. Then you go to basic image field. Okay, see here the bunch of function here. There is Gaussian field here. Okay, performing the Gaussian noise reduction. Okay, also there is a median field here. Okay, the only things they don't provide the average field. We need to construct the average field. In order to construct the average field, also we call the mean field, you need to use the field construction function called f spatial. Okay. For example, you can use f spatial to construct the mean field. This is show the field type is mean field, then the size. For example, you want to construct 3 by 3 mean field, then the h size will be 3 here. Okay, then you get the h. After you get the field h, then you call a special function called field2 to perform noise reduction. Okay, I'm sorry, noise reduction. For example, you use spatial 2, let's construct the average field. Okay, we want to construct average field. First step, get the average field h. So put average, we put 5. We want to construct a 5 by 5 field. After you get the average field, we perform noise reduction. Assume that the noise image is J. Okay. Then we do noise reduction. We can call a function called field2. Okay. Okay. Then we perform T is the result equal to field2. Okay, then h, then j. That's all. Then you will get the noise reduced image. Okay, but for the Gaussian and the median field, we don't need to construct the filter. They have a function MATLAB. You can directly use for noise reduction. Let's show some example here. Okay, first you get some image. It's called 8.tif. It comes with your MATLAB software. Okay, then you read the image to the matrix I. Okay, you can, this just show the image. Okay, for example, we can step by step show the image. Oh, okay, I'm sorry, there is a mistake here because the code symbol here is not correct. Okay, we just let's do this way. I already write down here. Okay, we just modify this one. Okay, you guys see here. First we read the image. Okay, to I, then we can show this image. This is the original image. Okay, we can step by step. Then show this image. This is the original image. I put a title here. This title function is used to show the information about this image. Then we add some noise. Use image noise. Add solid and purple noise to this image. We get the noise image J. Okay. For the image noise, you guys can go to the website to find how to use it. Okay. Then we show it. Okay, we show it in the figure 2. We still go here. We step by step. Okay, see, image 2 is this one. Okay, image 1 is here. So we add the solid and purple noise on the image. Okay, then we construct a min filter and perform noise reduction. First, we construct the edge. Okay, as we just showed now. Use this one. Okay. Okay. Then we put the size should be 3 or 5. We put 5 here. Okay. That's edge. After edge, we then perform the noise reduction. Use this one. Okay. That's the filter. That's the noise image. Okay. They will call the filter 2 function. Okay. Then we copy here. Let's see the result. Copy these 3. Okay, see here. Let's do some noise reduction here. Okay, 1, 2, 3. Okay, we get the 3. So let's go to use the median filter. See, median filter do the noise reduction is very easy. You just call the function called median filter 2. Then J is the noise image. Then we use J as input. Then the output K median will be noise reduced image. Okay. We also run it one by one. Okay. See, the noise is not there. So we have 1, 2, 3, and 4. Okay, 4 is shown here. Okay, 4 is shown here. So you compare the median filter is better than the mean filter. Let's consider use Gaussian filter for noise reduction. When you use Gaussian filter to perform noise reduction, also you can directly call the image Gaussian filter directly. Then you use the noise image as input. But here there is parameter you need to input. Do you remember when you talk about Gaussian filter, you need to select the sigma. Okay, so you do the Gaussian reduction. Okay, see, get the figure 5. Then we got all of the image. Figure 1, figure 2, figure 3, figure 4, figure 5. Okay, we just rearranged it. Okay, so now you guys compare. This is the original image. This is the image after you add paper and solid noise there. This is the result image you got use mean filter. Okay, this is the result image you got use median filter. This is the image you got use Gaussian filter. Compare these 3. You will find the median filter is much better than the mean and the Gaussian filter. Okay, that's for today.